Hi, my name is Bill Kinney, and this is part 4 of a series on large and small numbers, scientific notation, accuracy, and precision. That's kind of a long title, but I was actually even thinking about making it longer initially. I was thinking about adding the phrase errors to this, the word errors. Part of thinking about accuracy is also thinking about the size of your errors that you make and when you measure various things, when you try to make estimations. We'll think about it in the context of this problem here. The city of Minneapolis has a population of 383,000 people and a budget of $1.4 billion. How much spending is that per capita? That's the first question. And we're going to have a second seemingly unrelated question. Suppose a large family of 12 people moves to Minneapolis. What is the population of Minneapolis now? All right, focus on the first question. How much spending is that per capita? If you don't know, per capita means per person. And so that would think about what the units of that would be. That spending would be in dollars. Per capita is per person. So you'd want to take the dollar amount and you'd want to divide by the number of people. That ratio is going to be the spending per capita. Think about the numbers. 383,000 people. Does Minneapolis have exactly that many people? No. This is an estimate based on a census that was done a couple of years ago. I've rounded to the nearest $1,000 as far as how precise this number is. You would say it's precise to the nearest $1,000. It's got 3 significant digits. 3, 8, and the 3 there are significant. I'm assuming those are right. Doesn't necessarily mean this is accurate to $1,000 because the process for how that population was found could be off, or maybe because it was from a couple of years ago, this could be definitely wrong now. Could be off by a few thousand people, or even maybe 10 or 15,000 people for all I know. So again, it's precise to the nearest thousand. Hard to know how accurate it is. There is definitely going to be an error that comes about from taking the measured value, which is this 383,000 people, measured value, and subtracting the true value. Now, I should say true value with a caveat. That true value is always with respect to a certain instant in time, for example. So I could say this particular instant in time, which, just if you're interested, happens to be March 27th of 2012. There is a certain population here at 12:15 in the afternoon, and that true value would be what you subtract here from the measured value of 383,000 people to get the error. Could be a positive error, could be a negative error. Probably if this population is growing, then the true value is probably going to be bigger than the measured value, so the error will be negative. And if the population is falling, then probably the true value is less than this measured value from a couple of years ago, and so the error would be positive. I don't know what this is. You could make something up. You could pretend that the true value is 385,000. Then this difference would be 2,000. But it is still an idea that is sometimes useful to think about. There's also something called the relative error. Sometimes this error is called the absolute error, but you should not think of that as being an absolute value because it can be negative. This is called the relative error, and that's where you take the error and divide by the true value, whatever that happens to be. And again, you sometimes just have to pretend you know the true value, or pretend you've estimated it well, and you'd write that as a percentage typically. We're not asked to do that in this problem, but I just wanted to bring it up. Let me bring up one more thing about this, and that is that errors can be both systematic and random. A systematic error is when you consistently, for example, maybe overcount people because you're counting people twice for some reason. Maybe they live at a couple different homes, or maybe they live at college and home, and somehow you're counting them twice. That would cause this number to be bigger than it should be. That would be a systematic error. And random error just comes from mistakes in counting. Sometimes you might count too high or count too low, or in weighing you might weigh too high or too low because of the scale randomly being off a little bit. Those are the two sources of errors. All right, let's get to the questions. How much spending is that per capita? You've got to take 383,000 people, or excuse me, $1.4 billion. I'm going to go ahead and write this in scientific notation to emphasize that. A billion is 10 to the ninth, so in scientific notation, $1.4 billion would be 1.4 times 10 to the ninth. I'll write a dollar sign here. This ratio, divide this by 383,000 people, which I'll write in scientific notation as 3.83 times 10 to the fifth power, is going to be the per capita spending. Just a little more practice with scientific notation here. You can actually, type these numbers in your calculator and do the division as is, but it is sometimes useful, especially when you have bigger exponents or smaller if they're negative exponents, to actually do the division of the 1.4 and the 3.83 here first. So you can write it out. I'll go ahead and write out all those decimal places just to emphasize something. 0.3655, 35248. 3 there. And then you can divide the powers of 10 as well. And you would subtract the exponents. 9 minus 5, it would be 10 to the fourth power. But now we should round this to the correct number of significant figures. And the rule is when you're doing a multiplication or division of two different numbers, two different measured numbers, what you want to do is you want to round your final answer to a certain number of significant digits, and that number of significant digits should be the amount of significant digits that the least, that is, you've got the two numbers here, which one has the least number of significant digits? That's what you want to round your answer to. This one has 2 significant digits, this one has 3. We want to round our answer to 2 significant digits here. And so that would be, well, with this it would be about 0.37 times 10 to the fourth power. Round that 6 up to a 7 because of the 5 there. That's also 5s after that. And that's not the traditional way to leave it. You typically, as a standard thing to do, you want to have 1 digit in front of the decimal point. So you'd want to shift the decimal spot 1 spot to the left. And if you think about it, that's got to reduce the power of the 10 by 1. That's a bigger number there. So to compensate, that's got to be a smaller number there, is an intuitive way you can think about it. And how much we reduce the exponent is the same as the number of places we shift the decimal, in this case, to the right. And in ordinary notation, 10 to the third is 1,000. So this would be 3,700. Don't forget your units, dollars per person. There's your per capita spending, your per person spending for the city of Minneapolis. It's an approximation. It's not necessarily the exact answer. All the numbers involved are estimates. This definitely could be off, but based on the information we have, that's as good as we can do. Second question, suppose a large family of 12 people moves to Minneapolis. What's the population of Minneapolis now? You'd be tempted to say, well, 383,000 plus 12 is 383,012. And that is true as far as numbers go. Okay, I'll go ahead and write it down here. 383,000 people plus 12 people. As far as the numbers go, that does equal 383,012. But as far as what you should report, as far as what you should round when you're adding or subtracting numbers that are measured. You should round to your answer to the same precision as the least precise of these numbers. With multiplying and dividing, you want to round your answer to the same number of significant digits as the measurement with the fewest significant digits, which in this case was 2. So you want to round to 2 significant digits here. Here you want to round to the same precision as the least precise. This one's precise to the nearest 1,000 people. This one's precise to the nearest 12 people, or the nearest person, excuse me. And therefore, you round your answer to the one that's least precise, the nearest 1,000 people, which would be still 383,000 people. So what we're saying here is essentially the 12 people, this one family, this large family, doesn't change the population. And this should make intuitive sense. 12 is so small compared to 383,000 that yes, even though technically the population changes, as far as what you report, if you were giving a report based on this information, you wouldn't want to change the amount that you report, because this is to the nearest 1,000 people, and we're likely to be off by, you know, up to 500 people or something if the method for finding this population was a good method. So 12 people is not going to make a difference as far as 500 people. And that's what I wanted to get across in this video.